Today we're very happy to have two early career speakers giving us some talks. So we have first up Ofelia Bonesini, sorry Ofelia, from Imperial College London, who'll be talking about rough volatility, path-dependent PDEs, and weak rates of convergence. Given the time, let's save questions until the end, but people are free to post in the Q&A as we go along. Ofelia, please take us away.
Okay, thank you very much. I think I have something like half an hour, right?
Including questions, yes.
Okay,
so
perfect.
You can keep a bit shorter.
Yeah, I'll try to stay within the time given. So, well, first of all, thank you very much for the invitation, and huge thank to Crystal, well, who's not here, unfortunately. But let me start. So this is actually work that I didn't do by myself, but it's a joint collaboration with my postdoc supervisor, Professor Antoine Jacquier, and former PhD student and postdoc of his, Alexandre Panier, who's right now maître de conf at Université Paris-Cité. Now, the title, as you said, is Rough Volatility, Path-Dependent PDEs, and Weak Rates of Convergence. So a very long title for a very long paper in an even longer and still ongoing project. But let's start from an introduction to introduce the key ideas of the problem. So the setting is the one of rough fractional stochastic volatility models, and I think that we are more or less familiar with stochastic volatility models, so models in which the volatility of the log stock price is a stochastic process itself. These are extensions in which the volatility is not just driven by a standard Brownian motion, but by a process that we call rough. What does this mean? Well, this means that its sample paths are not h order continuous with h being at least 1/2, but with h being somehow a little smaller. And why are we saying and using this kind of models? Because this idea has been supported in the literature, both by some empirical work, but also by some theoretical studies. But this is not the focus of today's, because today I'm gonna take somehow as an assumption the model that you see here. So my starting point is going to be a rough volatility model where you see the log price is given by this x here. And the key point is that the process driving the volatility is this v here, where the kernel, which is a power function, is making it rougher in the sense that its sample paths are going to be h order continuous, with h being smaller than 1/2, as you can see. Another thing which is worth mentioning maybe is the fact that if you set h to be equal to 1/2, this just reduces to the standard Brownian motion, and actually this v here is not a random rough process, is actually the Riemann-Liouvin version of fractional Brownian motion. Now, in general, for the applications we have in mind, since there's no closed formula for pricing in this type of models, what we do is we simulate them. We simulate them via a discretized version, and in particular the first discretized version of the model you can come up with is a Euler discretization, a standard one, where we actually exploit the fact that the Gaussian process V as covariance function with explicit form, and this implies that it can be sampled exactly using Cholesky, and so we have a very nice way to actually write the Euler discretization. Now the point is that until and unless the softwares are going to become able to handle infinite quantities in a finite time, what is actually justifying the fact that for our applications we use this discretized model instead of the continuous version that was established in the beginning is the numerical analysis. So in order to assess if our approximation is somehow a good one, the first thing that one might be tempted to have a look at is the strong rate of convergence of our approximation to the original model. What's this? Well, this is nothing else but the L2 distance between the original process and the discretized one. Now, in our case, it's pretty simple, the computation we have to do. So we start from the fact that V is just H order continuous, and by a simple application of the Ito formula, we very quickly realize that the rate can be nothing better than just H. And what's the consequence of this? Well, the consequence is the fact that if we just want to divide our error by 2, we have to multiply the number of points we consider in our time discretization by 2 to the power 1 over h. And I didn't mention this in the beginning, but the estimated value of h is very small. In particular, in general, is taken to be close to or even smaller than 0.1. And this actually means that essentially the approximation is not converging. What's nice, though, is that for the applications we have in mind, which are in particular related to pricing, what's important is this type of error going under the name weak rates. So what we have to look at is test functions, because we are interested in the difference between the expectation of our test function evaluated at the original process and the expectation of the same text function evaluated at the discretized one. This type of rates are in general behaving way better than the strong counterpart, and in particular for our reference Markovian case, which is the case in which we just consider the Brownian motion, we know that despite being the strong rate just 1/2, the weak one is 1. So the question arises in a rough volatility as in a pretty natural way, and it is this rate now 2h, 1/2 plus h, 1, or something else? Well, we started our project thinking that actually this should have been a very easy question, if not trivial, but we soon realized that this was not the case. Indeed, once h is not 1/2, it's not that V is no Markovian. V is not even a semi-Marty anymore. So you actually lose tractability in the sense that you lose all the tools that you would in general exploit in order to get these rates, which are PDE methods and Ito calculus in the classical sense. Now, the literature right now on the topic is not that small, but okay, let's forget about the first couple of work, because these are in a very restrictive setting, as they are assuming psi, which is the volatility function, to be linear. For these two work, they are strictly relying on the structure for their computation, which are actually very specific for the model established. And in particular, in this last case, they are working by induction, what we wanted was actually methodology suitable to be extended, and extended in general even to stochastic Voltaire equations in general. So what we came up with, so what we did in the paper and what I'm going to present to you in this talk is that we first established a path-dependent PDE for rough volatility models, which is based on the Ito formula developed by Vian and Zhang. And then we have applied this to the computation of weak rates of convergence. Now, this is the result we have obtained, and for the sake of consistency with what is present in the paper on arXiv, I've left this assumption here, but actually a referee made us notice that it's not actually needed because it's automatically guaranteed by some regularity assumptions we have. Now, let's move back to the PDE first. So in order to give to you an intuition on how this path dependency is working, let's start with Vian and Zhang idea. Now, what they focused first on was this type of conditional expectations, because they soon realized that being this process X norm Markovian, expectations of this form were to be path dependent. But the question was, how is this path dependency actually working? And the answer can be found just writing V, so decomposing V in a suitable way. So the idea is to rewrite first X, exploiting its integral representation from T onwards, and then rewriting the process V, decomposing it not in the standard way that you would do in general, so as V T plus Vs minus Vt, because these two are not independent anymore, but rewriting it in this way, exploiting the integral version of itself, because now you have that theta t is actually something ft measurable, yit is independent from the filtration at time t, which intuitively is telling you that expressions of this type are depending on the filtration at time t just via xt and theta t. So this is, at least formally, the intuition behind how you can disentangle the path dependency in expressions of this form. Now, if we go back to our process X, now considering something a little bit more general, so a general stochastic Voltaire equation, where for simplicity I drop the drift, and we consider theta t to be nothing else but its ft measurable projection. What Vian and Zhang showed is that functionals of the concatenation of X and theta do solve Nito formula, which is very similar to the one we are all used to, but the fact that the derivative in space is now replaced by these pathwise derivative that are, in this particular case, taken in the direction of our kernel. Now, for the ones that are actually familiar with Dupuytren's derivative, this can be considered a generalization of it. Indeed, in Dupuytren's case, we are actually taking h to be 1/2, which corresponds to k being identically equal to 1. And this is because the path we are considering are not frozen, but just perturbed after t. Now, functional Ito formula, but an Ito formula in general, is naturally leading to a PDE that in our case is going to be a path dependent PDE, given the fact that we have this path dependency that I just presented to you. And indeed, this is what we got, because we have now that you can show the validity of such a PDE that is, again, very similar to the one we are all used to, but the fact that, again, the derivatives in space are replaced by pathwise derivatives. And this is very nice because it's providing us this is providing us with a useful way to represent conditional expectation. I said useful because in particular for our application to rough volatility, we have that now we can prove that the model that I presented to you in the very beginning falls in the I mean, it satisfies the assumptions needed for the validity of the results that I presented to you. And so we have that conditional expectations of functionals of the log stock price at the terminal time, where they are the unique solution of a path-dependent PDE that we can explicitly write, because we have actually representation, an explicit representation, which is quite long for all these terms, so I omitted it, but they can be written in an explicit way. And we also have the natural terminal condition, which is nothing else but a payoff function for your option. So, as I told you, this was somehow just establishing a tool in order to get to our final objective, which was the computation of weak rates of convergence for rough volatility models. So going back to weak rates, the first step in computing them via these tools is to rewrite them. So the difference between the two expectations as a sum over differences between the expectations of U evaluated at two subsequent points in the discretization. Now, all these AIs can be rewritten exploiting first the functional Ito formula in order to write them in their integral form, so as integrals, and then the PPDE to get rid of the term which is actually involving the derivative with respect to time. Now, now that we have these AIs, these are fine, but there's a problem in the fact that we have an expectation of a product where we would love to have the product of two expectations, because the terms for which, if you remember in the beginning, we add some upper bounds giving us a nice rate, in particular 1/2 plus h, where expressions of this fall. So we should find a way, a nice one, to disentangle these two. And we tried different techniques, the standard ones, and they were not working. And indeed, what's working is somehow a non-standard combination of the ingredients that you see in these slides here. So what we did first was a joint chaos expansion, which is needed to do what I was just telling you, to rewrite the expectation of our product as the sum of products of expectation. Now, the second ingredient is some Machiavellian calculus, which is needed to rewrite the terms in green. So the expectation of this term here, highlighting the dependence on the kernel. And finally, the last ingredient, but not least actually, is some combinatorics. And this is needed because, okay, now we have disentangled the two, making this product of expectation, but at the price of considering now series, so an infinite summation, and we have to show that this is actually converging. And how do we do this? Well, this is working because we have some bounds on the BDG constants that are appearing almost everywhere. And also we know the cardinality of the set DNK, which is the set in which the Malyaven operator D belong to. And in particular, this is the Stirling number of the second kind, and this is what is guaranteeing the convergence of the series. So now I cannot prove this in a more formal, rigorous way, but trust me, what you end up with are just integrals of this form here, which are yielding the nice rate of 1/2 plus h that we were hoping for in the beginning. So this is essentially the idea on how the proof is working. And to conclude, let me just sum up what we have seen and what are our ideas for the future. So we were able to establish a path-dependent PDE theory for stochastic Volterra equation, which is in particular applying to rough volatility models. And we have provided first application of this theory, which is the computation of weak rates of convergence, proving that for a wide range of models, this is actually at least 1/2 plus h. Now, there are actually a lot of directions stemming from this that can be pursued further. Just considering, just staying close by to this problem, one can first ask himself is if it is possible to actually obtain the rate that was somehow proved to be optimal for polynomials, which is 1/2 plus 3h, because it might be that because of the difficulty of all these computation, we missed some of the coefficients at some point. Then there's another question which is somehow pretty straightforward, which is can we actually include other discretization within our study, which in particular refers to the fact that one might be interested in having a look at the hybrid scheme, so possibly at discretizations of the process V itself. I think it's possible. It's more than the fact that the paper was already pretty long, and this would have taken more than a few pages. And the same is true for the drift, which has never been treated in the literature. It shouldn't be too complicated. It's actually more regular than the other terms. It's just a matter of computations. What's more interesting is the extension, at least in my mind, to fully implicit SVs, because for this I have sincerely no clue on what could potentially be the rate. And finally, as we all know, historically, the PDE theory has been the ground for many applications, ranging from stochastic control and optimization to integration by parts, but also, involving numerical methods as well. So I wonder if this path-dependent PDE theory can be somehow the starting point for a similar application, but in this extended setting. And actually, there are already some examples. Alex recently did something for path-dependent payoffs involving the VX, and Jack had some papers on numerical methods. So I think that actually, yeah, it's a field that naturally yields itself to applications. So yeah, this is our hope for the future. And if you have more ideas about the new things that we can investigate with these tools, I'm open to suggestions. And I just conclude by thanking you for listening to the talk. Thank you.
Thank you, Ofelia. So we've got a few minutes for questions. Do we have any questions? If you post them in the chat or the Q&A, or raise your hand and we'll allow people to speak. So I was wondering, the other thing that one can think about is trying to build some sort of approximate Markov process for these types of problems. So to lift the problem, to build in all of that path dependence just in a relatively low dimensional process that you use.
Actually, I think this is the approach of this paper. This one.
Okay.
This is the approach of this paper. So it's working or at least it was working when this psi was linear.
Mm-hmm.
I'm not sure. At first we tried to pursue this further, but it was, I don't remember what was the problem. But it was not working for us, or at least we found it simpler to just refer to PPDs. But yeah, I think that this is actually the path pursued in this paper.
So we have one question from Salah. Let me just find Salah. Salah, do you wish to ask your question?
Hello to everyone. Hello to everyone.
Hello.
Yeah, my question here, there's just one theorem in here. The name of this is this approach. There's some in the back. There is some theorem. Here is U is the method of decoupling field, or maybe KIC method, Feynman KIC method.
Sorry, I'm not sure I can hear you.
Please, there's a theorem in here. Can I?
This one?
To find, yes. Yeah. To construct in here U, it's the decoupling field, or maybe Feynman KIC method, or like this. I didn't understand.
So are you using a decoupling field in the construction of this theorem?
Yeah. Construction of decoupling field of Feynman KIC method, because to construct U must satisfy the following semi-linear partial differential equation.
Yeah, it's obtained by approximation, I think. Yeah.
I think like the Feynman KIC method, decoupling method.
Yeah, but I mean, we just use this result. This is not something we are proving.
Okay, thanks.
I don't.
Okay.
I'm not sure.
I think for the sake of time, we may have to move on so that Joe has time. Ofelia, thank you for the talk. Joe, do you want to start sharing your screen?
Yes.
Yep, if you just go full screen. Excellent. So our next speaker is Joe Jackson from Chicago, who's speaking about sharp convergence rates for mean field control on the region of strong regularity. Joe, take it away.
Yeah, thanks very much, Sam, and thanks to all the organizers for having me. I'm really pleased to be here and get the chance to share this talk. So convergence rates for mean field control is something I've been working on with several different people for several years, but I'm talking about mostly the latest installment in this series. which is a joint work with Pierre Kardali-Gay, Takis Suganidis, and Nikiforos Mimikos Stamatopoulos, who's a PhD student with Takis here at UChicago. All right. So I think that, you know, in the interest of time, I just want to jump in and start telling you about the model that I'm looking at. Okay, so I'm guessing most of you have heard of the topic of mean field control. And the basic idea is that you have a control problem, which is very high dimensional, okay, in the sense that there's sort of two ways to look at it. Either you think there's one central planner, so one guy who's in charge, if you like, of managing a whole bunch of different particles or state processes. And so to talk about this M particle problem, so each of my state processes, or each of my particles, if you like, is going to live in RD, okay? And then capital N is going to be the number of particles or the number of state processes, if you like, under management by this central planner. So D is the dimension of each particle, N is the number of particles my central planner is thinking about. And the data that I'm going to use to define my optimization problem in this setting just consists of three functions. So I have a function L, which I'm going to call a Lagrangian. Okay, that's a function on RD cross RD. And then I'm going to have two functions, which are going to be sort of mean field costs, F and G. So those are going to be real valued functions defined on the two Wasserstein space over RD, okay, which I'm calling P2 of RD. So I'm not going to spend the time to list out the precise assumptions I'm making on the data, but basically what I want you to think is that all three of these objects, L, F, and G, are quite smooth. Okay, F and G are smooth in the sense of calculus on the Wasserstein space, as developed in the theory of mean field games by Leons and others. And L being a Lagrangian, okay, I'm going to take it typically to be convex or even strictly convex in its second argument, okay? And so if you want to think of L as just being a quadratic function or a perturbation of a quadratic, as I've written here, that's totally reasonable for this talk, okay? So if you want to just have a quadratic Lagrangian in mind, that's fine. You won't lose much. All right. And then in my N particle problem, as I mentioned, my agent, my central planner, is going to get to choose how to control N different state processes, X1 through Xn. Okay? And he's going to control each of them linearly through the drift. Okay? And then there's also going to be a different independent Brownian motion hitting each state process. Okay? So this is just a really simple model where each of the N particles is controlled linearly through the drift, and then they get hit by IID Brownian motions. And my central planner wants to choose these linear drift controls so as to minimize a cost functional, which looks like this. Okay, so I've got a running cost in here, which breaks up into two pieces. One piece is an average, okay, of costs coming from each state and action pair. Okay, and this is dictated by that Lagrangian function L. So again, if you want to think 1/2 alpha k squared here, that's fine. And then another piece, which is determined by the configuration, right, of all the particles. So here I'm using mxn to be the empirical measure associated to the vector x. And then I also have a terminal cost, which is also of mean field type. So it depends on the positions of the particles only through their configuration or through their empirical measure. Okay, so that's my N particle stochastic control problem. It's written in a funny way because it's through these mean field costs, but at the end of the day, it's a standard Markovian control problem. And so I'm going to do a very, common move, which is I'm going to record the value function of this stochastic control problem. So my value function, I'm going to call Vn. that's a function on 0t cross rd to the n, because I have n particles each in rd, so my full state space is rd to the n. Okay, and it's defined just by, okay, for each possible pair of initial conditions, I minimize the cost functional over admissible controls. And everything here I'm going to assume to be reasonably smooth, so there's no problem in saying that Vn is in fact the unique classical solution to the corresponding Hamilton-Jacobi equation. All you have to do is work out when you have the total Lagrangian from the previous slide is sort of this average of the Lagrangians as corresponding to each state. And so you have to work out what's the sort of full Hamiltonian. It turns out the full Hamiltonian in this equation is also sort of an average, except you have this factor n inside the Hamiltonian in front of the gradient. Okay, so you follow the usual recipe and you write down this Hamilton-Jacobi equation for Vn, okay, which is somehow an n-dimensional Hamilton-Jacobi equation if you want. Okay, so you want to send the number of particles to infinity, because it's not the sort of purpose of this talk, I'm not going to spend too much time on a heuristic derivation of the limiting model. But basically, in the limit, you imagine, okay, all right, so instead of choosing n different drifts, I'm just going to control one state process x. And somehow the law of x is going to be a proxy for the distribution of all the many, many particles. So I choose my drift control alpha. Okay, and with this interpretation in mind, my cost functional I seek to minimize is going to look a lot like the one from before, except that average of Lagrangians is going to just wash out by a sort of law of large numbers to just the expectation of L of x alpha. And everywhere I have the empirical measure of my very high dimensional state process before, I'm going to have the genuine law of the unknown process, or sorry, of the controlled process x. So okay. You can see that this looks a lot like a standard stochastic control problem, except I have the non-standard feature that the law of the controlled process x is entering the cost functions. And because of this feature, a natural thing to do is, instead of defining the value function as a function of t and x, okay, in order to maintain time consistency, I should define the value function as a function of t and the initial distribution of the controlled process x. So in other words, this time, when I go to record the value function of my stochastic control problem, I'm going to get a function over 0t cross P2, the two Wasserstein space. Now, just like with finite dimensional stochastic control problems, tools have been built which let you derive, formally at least, a Hamilton-Jacobi equation that we expect you to solve. I'm just going to write it. I'm not going to talk too much about exactly what these derivatives mean. I've chosen to write the equation in terms of the so-called linear derivative. So this du dm here, okay, is the so-called linear derivative of the function u in the argument m. It's sort of like the derivative you get when you think of u of the set of probability measures as a sort of flat space, a convex subset of the space of distributions or something. Okay, so we can write it down. I'm not going to spend too much time talking about the analysis of this Hamilton-Jacobi equation. Let me just say that the well-posedness of this equation in the sense of viscosity solutions is an open research topic which has seen a lot of attention recently. So, okay, we expect to be able to say that U is in some sense the unique viscosity solution of this equation. okay, I'm not going to worry about defining exactly what I mean by viscosity solution here and talking about that literature. Okay, so I just want to quickly, the main topic of this talk is going to be the convergence problem. But let me just list first a few facts about the limiting model we're talking about. So under the standing assumptions, the end particle problem is qualitatively quite well behaved. There are unique solutions. Vn is a smooth solution to the Hamilton-Jacobi equation. You have what you want, but it's hard to get any useful quantitative estimates, for example, on Vn or the stability of the optimal trajectories, which are uniform in n. So that's part of the reason why, even though Vn is perfectly nice, sort of theoretically, qualitatively, it can be difficult to work with. As far as the limiting model goes, under some standard conditions, for each pair of initial conditions, you can definitely find at least one optimizer for the minimization problem. And in fact, you can say more. You can say that any minimizer is corresponding in a particular sense that I've written here to a solution to the corresponding MFG system with which is a certain forward-backward PDE system. And you can use this fact to infer that actually any minimizer has some amount of regularity, at least in the space variable. So there's at least one minimizer. Any minimizer is actually a smooth feedback control. Okay. But in general, there are examples showing that there could be multiple minimizers. Okay, so you lose somehow uniqueness in the limiting model. And we only expect to have uniqueness when the cost functions f and g are in an appropriate sense convex. And this last point I'll get back to later, but quite related to the lack of uniqueness of optimal trajectories is the fact that we don't, in fact, expect U to be a classical solution to the infinite dimensional Hamilton-Jacobi equation I wrote down in the previous slide. Okay, so let me get now to summarizing what I mean by the convergence problem and saying what we know about it. So we know, we expect this end particle model is in some sense converging to the limiting model, but what does that actually mean? Okay, and there's a number of ways to interpret that convergence statement, but the one I'm going to focus on today, which is convenient in many ways, is to say that the value functions converge in the sense that evaluating Vn at a vector x should be like evaluating U at the empirical measure associated to x. So you get this version of convergence. And it turns out that this statement, that Vn is converging to U, has been known qualitatively for quite a while and in quite a bit more generality than what I'm presenting here today. The first paper in this direction was from Dan Lacker, and then there was an extension to include common noise by Jete, Possamay, and Ten, and another paper by PDE techniques by Gangbo, Mayorga, and Schweich, which dealt directly at the level of the Hamilton-Jacobi equation. So because of these papers, under a great deal of generality, we know that the statement I wrote at the top here, Vn being approximately equal to U, is true. But all of these methods somehow rely on compactness, and so they do not and really cannot come with a rate. So as applied mathematicians, we know that these Vn's converge to U. So of course, the next question we want to ask is how fast? So how fast is the value function Vn going towards the value function U? In general, this is a hard question, but there's one regime I want to explain where this is relatively easy. So if you just assume that somehow you know that the limiting value function is smooth, then you can do an explicit computation using calculus with these infinite dimensional derivatives, and you check that UN, which is the projection of U down to finite dimensional space, solves the exact same Hamilton-Jacobi-Bellman equation that Vn did, up to an error term, which is written explicitly in terms of the so-called second Wasserstein derivatives of U. Okay. So whatever this derivative means, okay, we can just look at this expression and see that if dmmu were bounded, right, then here I would have a sum of n bounded terms, okay? I have a sum of n bounded terms, and then I would divide by 1 over n squared, okay? So you use the comparison principle and say, if this error, so if this dmmu is bounded, the error term is of order 1 over n. Therefore, by comparison principle, Vn and Un, which is the error we're after, is bounded. It's of order 1 over n with an explicit constant up to the size of this second derivative. So that's great. But unfortunately, in general, it's just not true, even if all the data is really smooth, that U is going to be smooth. And there's an example that I like to use to illustrate this fact, which is you take your, sorry, I've switched from script F to capital F and script G to capital G here. That's an accident, my fault. So you take your mean field coupling functions, F and G, your mean field costs, and you assume that they just depend on the mean, right, the mean of the measure M. And then you check that actually that property is going to be preserved by the equation. So you're also going to have that the value function U is a function just of the mean. And in fact, the function little u that it factors through is going to be the solution to a finite dimensional Hamilton-Jacobi equation. And the thing you should notice is that there's no viscosity. There's no Laplacian appearing here in the equation for little u. So I'm going to skip this discussion of Vn in the sake of time, but what I want to point out is, okay, even if you have the independent Brownian motions, somehow their smoothing effect in the limit is washed away. And that can be understood by this fact that if you have just mean dependent cost functions, then you wind up factoring through the solution to a first and not second order Hamilton-Jacobi equation. And so because we know that these first order Hamilton-Jacobi equations have, in general, have Lipschitz solutions, but the solutions aren't C1, we can infer that the same is in general true for U. So in general, this function big U, we can expect it to be Lipschitz, but no better. So I think the next natural question then is, okay, we know that everything works nicely and we have the right 1 over n if we assume that U is smooth, but we've seen that in general, U won't be smooth even if all the data is. It just won't be the case. So then you want to say, all right, what can you do in general? This was the topic of my first project on this in this area with Pierre Takis and Samuel Daudon. And so here's the main result from that earlier paper, which says that indeed, even if F and G are not convex and therefore U may not be smooth, you can have an algebraic rate of convergence of Vn to U. So you have a rate n to the minus beta d, where this exponent beta somehow depends on the dimension, but I don't want to get into this point. All right, so that's what's known so far. If things are smooth, you have the rate 1 over n. If they're not smooth, you have some rate which depends on the dimension, but is not optimal. Okay. And now I want to talk about the last portion of the talk is going to be about our most recent project. So I mentioned already that U is at best Lipschitz. It's not C1. But in a recent paper, Pierre and Takis identified an open and dense set of initial conditions, okay, which they call O, script O, where U is in fact smooth. So even though it's definitely not globally smooth, okay, somehow it's generically better than Lipschitz. It's generically C1 in the sense that it's C1 at least on an open and dense set O. The set O that give us a concrete characterization of It's a set of initial conditions from which you do have uniqueness of optimizers for the mean field problem. And the unique optimizer you get is stable, where stable has a specific technical meaning here in terms of the MFG system you get by linearizing around this optimizer. So it's by no means obvious with this definition that O is non-empty, let alone dense. But it turns out they're able to prove that this set O, which they construct, is open and dense. You have some additional smoothness there. So I think it's reasonable to ask then, could you localize in some way the argument leading to the 1/n rate in the smooth case, given that you have smoothness on this particular open and dense set? So that's what we did in this most recent project. Okay. What we proved is if you give me, okay, a set K, okay, it's a subset of O, which is compact in the P Wasserstein space for some P bigger than 2, then the rate is actually 1/n uniformly over the set K. So this constant C appearing here is allowed to depend on K. So you can get a different constant C for each K if you like. And I want to say this theorem is not just a consequence of the fact that U is smooth in this open and dense set O. The invariance of the set O is key, which means the fact that it turns out optimal trajectories that start in O stay in O. So this turns out to be a key. All right, so I think I just have like 2 or 3 more minutes. So I'm just gonna skip. We also have a result about the convergence of the optimal feedback controls, which is roughly translates to convergence of the gradients of Vn towards the gradient of U, which exists at least in O. But I think I'll skip this point. And I'll just say a few words about the idea of the proof. So I mentioned the idea is to somehow try to localize the proof that we know for the smooth case. Okay. So what we do is we look at an initial condition in O, and from that initial condition, we have a unique optimal trajectory. So what we do is we fatten up that optimal trajectory a little bit to form a small tube around this optimal trajectory. Okay, and then what we prove is if you take 2 concentric little tubes around an optimal trajectory, so you have, say, a tiny tube and then an even tinier tube, okay, the probability of exiting the bigger tube, decays algebraically, okay, uniformly over the smaller tube. So this is a technical lemma which somehow uses a bunch of the stuff we already know about convergence. But it still leads to a highly suboptimal exponent here. So it decays algebraically, but with a really poor rate. So then you say, well, how could I get from this suboptimal estimate of the probability of exiting a tube to something that's optimal? And the way we do it is an iteration procedure. So what we're able to do using the regularity of U inside the big tube is to say that the difference between U and V is like 1/n plus the probability of exiting the tube times, okay, the rate of convergence over that larger tube. And so finally, to conclude, what we managed to prove is that the rate of convergence improves every time you shrink to a much smaller tube. Okay. And it improves by a fixed amount. So in the end, we iterate this procedure a finite number of times, and we find that around each optimal trajectory, which originates in the set O, we can find a really tiny tube around that optimal trajectory where the rate has to be 1 over n. And this basically completes the proof because it almost, up to one technical detail, allows you to construct an open cover of the set O by these little tubes. One on each one, the rate is 1 over n. Okay, so by compactness, essentially, you get the rate. Okay, so that's it for me. I'm sorry that I sort of sped through the ideas of the proof at the end there, but I'm very happy to talk more and answer any questions.
Yeah, thanks so much, Joe, for such a wonderful delivery. My question is regarding the proof. So you mentioned that if you pick any optimal trajectory in the set, we are able to construct like a loop around it. And my question is, you mentioned that sort of the set is compact. And so the question is, does that mean the optimal trajectories are infinitely many in the set?
So when you're talking about the set, do you mean K, the compact set that we're proving the
Yes.
rate over, or do you mean O? You
Oh,
mean K.
no, O.
Oh, okay. Yeah, so the set O is open and dense. So yes, it you know, from each this is an open and dense subset of some infinite dimensional space.
Yeah.
From each point in that set, I have a unique optimal trajectory. And this optimal trajectory remains in O. So if I start in O, I can't leave it. So yeah, there are infinitely many different trajectories inside that O. O is not compact though. It was the set K.
Hey, that's
So it was the K was some compact subset of O over which I was proving the uniform bound.
okay. Thanks for the clarification.
Sure, yeah, of course. Thanks for the question.
So I'll read Rene's question. It's about optimal controls whose existence you proved early in the game. Can you prove they're bounded before working on the torus? In other words, do you know early if the gradient is bounded?
Yeah, so you want to know if, so does each optimal trajectory, is it a bounded feedback control? So the answer is, of course, it depends on, I never carefully said what my assumptions were. That's formally equivalent to the D1 Lipschitz continuity of the value function, which we can prove typically if F and G are D1 Lipschitz and the Lagrangian has some nice, the Hamiltonian has some nice smoothness properties. So, of course, it won't be true that you, so if everything is nice, you can get an L infinity bound in the controls, which I said is formally equivalent to a uniform bound on the D1 Lipschitz constant of U. Okay, but if you want to handle, I should say if you want to handle like linear quadratic type models, then you won't have a global Lipschitz bound. The Lipschitz constant is going to grow linearly somehow with the measure when you're on the whole space. So typically, if you want to handle something like that, you'll have a local Lipschitz bound or something.